In this video, we introduce the novel concept of surrogate Q-learning for the application of autonomous driving. Deep surrogate Q-learning uses a modular pipeline where a perception component extracts a variable-sized list of surrounding vehicles. This list can be extracted from either recordings of test vehicles or top-down images recorded by drones or from bridges. In deep surrogate Q-learning, we reduce the required driving data for training by taking into account actions and rewards of all vehicles in sensor range. In contrast to a multi-agent setting, in this work, rewards of other participants are computed according to our desired reward function. They are used to compute the value function of the test vehicle more efficiently. In contrast to transitions containing state, action, next state, and reward as in the classical RL setting, we now use scene transitions containing actions and rewards for all vehicles in sensor range. Then, we sample uniformly from the collected scene transitions and add all transitions from all participants into a large batch to update the Q value. The final policy is extracted by taking the action maximizing the Q value for the test vehicle. Using costly preprocessing, transitions of all vehicles could be taken into account by iterating through the dataset and, at every iteration, considering another vehicle as agent. Instead, we propose to use a very efficient and flexible permutation-equivariant deep neural network architecture of the action value function. The architecture, consisting of an encoder module, a scene module, and a Q module, is able to estimate action values for a variable number of vehicles in sensor range simultaneously in one network. We studied the number of observed lane changes in the SUMO traffic simulator. Observing all surrounding vehicles reduces the required driving time tremendously in order to collect the same amount of lane changes. Deep surrogate Q-learning increases the maximum performance by 15% trained on data collected by a test driver performing approximately 5% lane changes in 30 driving hours. For a driver staying on the same lane, the performance is increased by 58%. Here, the deep surrogate Q-learning agent acts in a highway scenario in the SUMO traffic simulator. The agent learns to perform lane changes in a data-efficient manner. The goal is to drive smoothly and as close as possible to a desired velocity. In contrast to the deep surrogate Q agent, the deepset Q baseline is not able to perform well on smaller transition sets and transitions collected from a test driver with 5% lane changes. Here, the deepset Q agent failed to change to a faster lane in time. In this video, you see the deep surrogate Q-learning agent trained on only 18,000 transitions corresponding to 10 driving hours. The transitions are generated from the HiD dataset with top-down recordings of German highways. The surrogate Q agent learned a well-performing driving policy, which is a major step towards the application to real systems.